Greetings, architectural structures enthusiasts in YouTube land. This is Professor Deborah Oakley at the University of Nevada, Las Vegas School of Architecture again. Today we are going to be looking at laying out a structural framing plan that is coincident with an architectural plan. This is an exercise that architects should be familiar with because where a column grid falls with regard to your architectural plan is an important consideration. We also need to be aware of parameters that affect the structures, such as appropriate span lengths and ratios of long size to short size for the structural system. Back in the day when I took the architectural licensing exam, it was pencil and paper, and this is an exercise that was required for that exam. So we'll be looking at two different systems here. One is a one-way steel frame system, beams and girders on steel columns, and the other will be a two-way flat plate concrete system on concrete columns. So we'll go through these step by step, and hopefully this will help you to understand the process better. So here we go. The first thing we need to do here in this drawing that I downloaded from the internet is establish a standard scale. So it doesn't have a scale on it. I'm going to pick a reference object. In this case, I'm going to use a doorway, which for accessibility reasons typically is going to be 3 feet in a public building. So I'm marking 3 feet here and then dividing that up into 1 foot segments. So I've got 2 3-foot segments. And what I'm really interested in is the 5-foot mark here. That's going to become my standard scale. So I'm transferring this 5-foot dimension onto another card, and I do that repeatedly until I get a scale of a desired length. So here's my first 5-foot mark, and then I can put dots in for the 1 feet, and then another 5 feet gives me a 10-foot mark, and then one more is 15, and then I keep on doing that until the whole thing is complete. So I've already completed that on a separate sheet, and I can use this now for scaling, and this is my standard scale. I can dimension this entire building with regard to that and have my structural framing system align with that. I see I've got about a 20-foot, 21-foot span to the wall on the inside, about 30 feet on the inside, so it kind of makes sense to divide that up into 2 spaces. So I'm working on a light table here. I'm going to overlay this with another sheet of paper and go ahead and tape that down so it doesn't move around. And now I can begin laying out a column grid according to that dimension. I'm going to start with the outside edges and work my way in. So this is roughly aligned with the outside edge of the building. I'm not too worried about the exact placement of that column grid relative to the wall right now. The column itself could be within the wall, it could be outside the wall, or it could be inside the building with a stub out. That's actually the most common, so we don't have an interference between the exterior wall and the interior. So I'm going to speed this up from this point out. So what I'm looking to do is align my column grid with major interior features, interior partition walls, and they're in natural locations in the horizontal direction. In the vertical direction, I want to recognize that there's a large auditorium space. I don't want any columns in, so I'm going to use the wall that bounds the office areas with this auditorium, and then use the first wall from the inside to make my primary column line. And so I actually have a column line that goes across the corridor on the right. And the other walls, I want to make sure that those columns do not fall into a window area or something like this. So I'm dimensioning my column grid, spaces in between the grid as well as the overall dimension. Put column heads on these. In the horizontal direction, I'm giving those letters, and then dimension those based on the scale that I previously created. And do the same thing in the vertical direction. Get center dimensions, put the column heads on, These are labeled by numbers in the vertical direction, putting my dimensions in between there. Really should be a little bit more space between those dimensions in the column heads, but wasn't sure how that would fit on the page. I kind of ran out of space. Now I'm installing columns on here. I'm just using squares to represent those columns, making sure I align these properly horizontally. These would be wide flange columns typically in a steel frame structure, but often they're tubes as well. We'll just represent them by the squares right now. So now I'm placing my girder line elements. I'll use a rolling ruler. Now notice the long span, I'm actually covering that with a larger element. This is going to be a truss element. I made a mistake there on line 4. I'll have to come back and correct that later. In the vertical direction, these are going to be my secondary members. So I start on the column lines, but I'm going to divide this in two. Now here's a trick for you. When you don't know the exact dimension of something, to divide it in equal spaces. Notice I'm tilting that ruler to thirds, and so that's actually splitting it up on the diagonal by thirds. That's a handy way to split an unknown dimension. I'm doing it here again on splitting in half, another into thirds, and then the last one also into thirds. So these spaces are not equal throughout the building, and that's quite common in any structure. And I wasn't quite sure how I'd do this, but I decided to keep exactly the same beam spacing between these long span elements, and then that covers the major framing. Here's my long span truss. So next I want to actually get the member depths, the approximate depths, based on rules of thumb. This again is for a steel frame system. So the guidelines I'm going to work with here are that for beams we'll use a span to depth ratio of span over 24. And then for girders we'll use a span to depth ratio of span over 18. So first we look at the beams. We really only have two beams. One is a 20-foot span. That's between lines 1 and 2, or excuse me, 2 and 3, and also 3 and 4. So that gives me an approximate depth of 10 inches, so we'll select a W10 member there. Now we don't know the size of that member until we actually do load calculations, but this gets us in the ballpark. That's the objective here. For 24-foot span, that comes out, again, span over 24 gives us a 12-inch beam, so we'll have W12s there. And then we go on to the girders. We have several girder spans. 19 and 21 are close enough. We'll just use the 21-foot span for that to account for both the 19 and 21. So 21 foot for both. So the approximate depth there, again, span over 18. 21 times 12 over 18 is 14. So that'd be a W14. Then we have a 26-foot span. So here we get a little bit of reflections there, 17.3. So that rounds up to a W18. Then we have a 30-foot span. And here that gives us a depth of 20 inches, so that would be a W20, but there are no W20s, so we'll use a W21 on that. And then the last one, I marked that as a 36-foot span accidentally. That's actually 34. Correct that later on. It actually rounds up to about the same. So for that 36-foot span that I chose, that comes out to an even 24. So we pick AW24 there. Then we want to estimate the deck. We look at the maximum span there. I've got 10 feet on the 30-foot span, and then 34 over 3 is 11.3, and that's the largest of all of those. So I'm going to, it's only 8 foot 8 for some of those, so I'm going to use the 11.3 feet. Now the ratio, I'm using this from the book, the Building Structures Illustrated book, and this is on page 123 out of that book, and that says a span ratio of span over 35 for the approximate depth. So I'm going to use the 11.3 feet, multiply that by 12 to get inches, divide that by 35, and that comes out to 3.87, so we'll round that up to 4 inches for our deck. Then lastly, we have the long span girder. And that span goes from line C to line F. That's 19 plus 30 plus 34. Comes out to 83 feet. And for a parallel cord truss, if it's a low load, we're looking at L over 15, so we'll use L over 15 for our depth. So that's 83 times 12 to get it in inches. Divide that by 15. That's 66.4 inches. Convert that back into feet, 5.53 feet. So we'll call it a 5 foot 6 inch thick deep member. Now the last step is to transfer this information to my drawing. I'll start with the deck. This is a 4-inch concrete deck on a metal steel form deck. Span direction is left to right as we draw this. Then the long span trusses 5 foot and 6 inches deep. And then the beams in the vertical direction, we have 10-inch beams. Made a mistake there, that's actually a 12-inch beam there. 10 inches in the center, 12 inches on the outside. And that's typical for all of these between bays 4 and 5 and 1 and 2, the 12-inch beams. And then between 2 and 3 and 3 and 4, those are going to be the 10-inch beams because that's a shorter span. And then between lines A and B, we have W14s. B and C, we have W18s. Between C and D, W14s again, same as A and B. And then the 30-foot span, W21s. And this is where I realized I made a mistake. That's actually 34. So if we calculate that, span over 18 comes out to 22.37. So I'm still going to go with the W24 there. And that's between lines E and F. And that really completes this layout. I did make a goof on my columns, so correcting those. And notice that the secondary elements did not run into the primary elements. I want to make sure that there's a separation, so there's a clear hierarchy. You can see that especially on the long span. And then turning on the backlight so we can see the overlay to the architectural layout below. Okay, so this is the second example here. We're going to use a two-way flat plate. This is our floor plan, another one that I've just grabbed off the internet. Again, this one I also had to create a separate scale for, which is already done. So this is a direct recording. The last one I did a voiceover so I could speed up a lot of those line drawings that are kind of tedious. But I think there's a lot of things that can come out in a direct recording that are hard to recreate because it's sort of spontaneous. So I'll do my best here to not go too slow on this. So turn on the light table. So this plan is deceptively complex to align a column grid with. And, where do you start with something like this? Basically with the two-way system, I'm looking for something that's relatively square. That is that we don't have a long side to short side ratio of more than 1 to 1.5 or thereabouts. You can go a little bit larger than that, but that's a general guideline. So what I want to do is I'm going to do two overlays here. The first one will be the exploratory grid, we'll call it that, and then I'll adjust that a couple of times. So let's start with the outside and work our way in. And I'm just going to draw these as red lines here. And so this sets up our boundary. Now, for what we're doing here, this is another copy out of the Architect Studio Companion. Put another sheet behind that, we can see better. So this is for side-cast two-way flat plates. And we'll assume conventional reinforcing, not post-tensioning, and a size that we'd like to have that's sort of middle of the road in terms of load, and recalling that the leftmost region is for heavier loads, the rightmost is for lighter loads, and then of course long span versus short span when we do horizontally. So middle of the road puts us maybe at about 25 feet and a slab thickness perhaps about 10 inches. And beyond 10 inches, that's getting pretty darn thick. You are going to start thinking about post-tensioning or maybe changing to a two-way waffle slab or a slab on beam, something like that. So we're trying to keep within 25 feet as we do this. Now, if I get up my scale, my total distance here is about 60, looks like about 62 feet or so. So twice 25 would be 50, so we're beyond that. So I want to actually divide this into thirds. And if you didn't catch what I was doing in the previous video, dividing up equal spaces, this is a trick I learned back when I was starting out in engineering. A drafter showed me this, very simple. I'm trying to divide this into three spaces. Well, I go from, let's set this so we can read it, go from 0 to 6. Every one space long here give me 6 spaces. So I go every 2 here and here, 2, 4, and now I've divided this into thirds. So let's stick with the red pencil here for a minute. And there are our 3 roughly equal segments. Now I'm going to do some fine measuring here with metric on my Las Vegas Springs Preserve ruler made out of recycled newspaper and plastic. Pretty cool. I want to use millimeters because it's just easier to read than sixteenths or eighths. So from here to here I've got about 42 millimeters, 43, looks like I was a little bit off on that one, but that's my thirds. So I'd like to get this into squares if possible. And if I look at 43 millimeters and just keep adding those up, I've got 230, well, let's do it this way. I have 238 millimeters in the long direction. And then in the vertical direction, again, I've got about 44. So I'm going to divide 44 into 235, 5.4. So I don't have a whole number of divisors or multipliers by 43 to get this length. So I'm going to round that down. I could go up to 6, but let's try 5. And if I take my 238, well, let's not even do it that way. Let's do it with the sloped ruler again. So if I want to divide this into 5, that means I need to do 10 units across. So now I took every second one, be right here, 1, 2, 3, 4. So 1, 2, 3, 4, 5 spaces. And try and keep these things parallel. Use a rolling, excuse me, use a rolling ruler. And I can see I've got some problems. So turn off the light table here. Maybe we can see both. Yeah, that comes through a little bit. But that one's okay. That's not so happy. That's a bad one. And that's a definite no-go, as is that one and that one. So we have to make some shifting around here. So let's take a look at what we can do to kind of try and match the proportions here, because I'm not quite 1-to-1 here, but it's close. I can massage this. I've got room to move back and forth. So I can probably move a line, probably these inner ones out a little bit, and we'll see what we do with the horizontal ones, and then try to keep that as close as we can to a 1-to-1 grid, but certainly not more than 1 to 1.5. In buildings of this nature, kind of a rectilinear plan with a core in the middle, the core is often a controlling element. Things work out from there. So we have a stairwell, we have an elevator shaft, probably a mechanical equipment closet at every floor level, and then the bathroom. So this whole thing kind of defines the core, and certainly the stair and elevator where there are heavy walls that are probably shear walls for lateral stability. So it's ideal if I could actually get into those walls. So let's shift this one over and see how that looks. I'm going to use a regular pencil here, and I'm kind of liking that. This column over here, I don't like it in this middle of this room. I mean, look at that. You just walk in the door and there's a column. Boom. So that's no good. What happens if we pull this line up? Because I'm kind of wondering what happens. You know, we have this column line here and there's a bathroom here. We might have to make some changes to the architectural plan to make the structure work. That's sometimes something we have to go back and forth between. So this is okay, but remember the column has dimensions, maybe depending on the size of the building, but we'll say it's an 8x8 column, maybe a 2 or 3 story building. There has to be some shifting with this because the plumbing wall is going to run into the column. But that may be the best we can do here, unless we take it a little bit further. But now we've got a window out here. So there's always this back and forth in the initial planning stages between architecture and structure as we do things. And mechanical, of course, is in there as well, such as this area with the plumbing. But we'll just try and line this up as best we can here for the purposes of this example. So the same thing's happening over here. This is a okay location with regard to that closet. Not so good here in the middle of the toilet stall. So maybe we pull this back, and I see there's an alignment here. See where we go with that. That puts me to the edge of the window here, and that's okay. You know, think about what's happening here. That there might be an enlargement area with the column, and this is symmetric on the facades. That's actually a good thing architecturally. But this is not good now, so we need to rethink about that. So if we pulled the column line down here, not so good, because now we're talking about a rectangle. That's not the right proportions. What if we actually introduced another column line? So it really is a back and forth kind of play between architecture and structure. You have to say, well, is that okay or not? And how are things lining up? It actually, I did several experiments here and came to the conclusion that for this one, without making more changes architecturally, I want to actually split this up into something closer to fourths instead of thirds. And so that gives me another column line right along here, and then one more down here. And I can keep that one, which came close to falling on those walls, and then I can put one right here. And I see some symmetry on the facade. This is actually not horrible. So we've got columns here. That works in that closet, against a wall, corner here. No, not one there. Right here. No, that's okay, and that's good. Yeah, this is working out okay. Now, what about the ratio here? The long side to the short side. That changed a little bit. It's not square anymore. And how long are these things, too? So bays are actually getting kind of small, 15 feet. If we go back to our sheet for column size, the grid size, 15 feet is actually getting to be on the small side for a two-way flat plate. But it's okay, and again, this is illustrative for the exercise. So 15 feet this way and 25 feet that way. So that ratio, turn off that so we have front light. So 25 divided by 15, 1.67. A little bit bigger than 1.5, but I'm going to call it a day and say that's close enough for what we're doing here. So that's going to be our basis grid, and we're going to draw the real grid. So I'm going to do one more overlay here. Now I'm going to do this grid here sped up. Just one comment about column grid lines. They are drawn as light dash dot lines because that is to clearly differentiate them from other line work in drawings. The column grid is a background element to all drawings in a contract document set because they underlie not just architecture but structure, mechanical, electrical, plumbing. Everybody refers to the column grid. Column grid is the first thing that is set out when the building is constructed because that represents where the footings are going to be put down and where the foundation, not just footings, but whatever foundation it is. Okay, I'm going to stop talking here and speed this up in production. Okay, so now I have removed the underlay sheet and completed my grid, indicated the columns, and let's turn the light table back on. We can again see how that coordinates with the architecture. One thing that's important is uniformity. So we have a lot of 21 by 15 foot bays. That works out great. The 16 foot, that's awful strange. So you know what, these should be all the same. That's another adjustment we might make. But having two long and then two short and then one long and two short again, that actually is okay. So that I'm not bothered by that rhythm at all. the 25-foot span, that is the outlier on this. So I'm kind of rounding down a little bit and saying that 9 inches, which works for a 21-foot slab. Now there's a couple of things that, just FYI, I don't make this a part of a student exercise, but we do have penetrations here, right? There's stairway right here. There's the elevator right here. And this poses very interesting challenges right off, because the way a slab is reinforced commonly is to have embedded reinforcement that mimics a beam, even though there's not a beam in there. It's the same thickness. So let's let this represent the reinforcement for a slab. At a column grid, we're going to have multiple bars there clustered together to give it extra strength. Then we get further away towards the center and it spreads out a lot. Now, that's extreme, but just as an example. So what we don't have here is a band. It's actually penetrated. So that's an excuse me, another consideration we need to take into account. And that really would affect this column line here. There's also a cutback in the slab here at the opening. This is actually relatively easy to accommodate because we would have multiple reinforcing bars right here and some right here. That forms our beam band. These are actually called column bands, I believe. Column reinforcing bands. And so we have one right here. And the break, well, we have to make elements kind of cantilever across here. We can put some extra reinforcement right here. This is a long way to cantilever, so I think we're going to have to double cantilever. So reinforcement would go over here, and this would actually go over here to carry that. So they work together, and that's how we'd be reinforcing an opening. Now, architects would not really ever be responsible for this, but this is what our structural engineers need to think of. But in terms of just coordinating a plan, becoming aware of the impact of where your columns are for a given structural system and laying that out, coordinating with the architecture, that's the intent of this particular exercise and look at coordinating architecture and structure. So I hope that's helpful. Thank you.